First, I want to say thanks for the opportunity to speak at this conference today. I'm Andrew, and I'll be presenting on a data-driven chemical heuristic for electronic topology diagnosis. And this is joint work with Yang Zhang, Thomas Christensen, Huitren Po, Li Jing, Liang Fu, and Martin Soljacic. So some people in the audience may already be quite familiar with this topic, but just to make sure we're all on the same page, I'll start with a little bit of background on topological materials. The setting of today's presentation will be three-dimensional crystalline materials that we can understand using band theory. So in this setting, loosely speaking, we can think of there being two important broad classes of topological materials: topological insulators and topological semimetals. Topological insulators have a band gap and non-trivial topological invariant. Includes Z2 topological insulators, topological crystalline insulators, and higher order topological insulators. And topological semimetals have band crossings protected by symmetry or topology near at the Fermi level. And some well-known examples are Weil semimetals, Dirac semimetals, and nodal line semimetals. And one of the core reasons we should care about topological materials is that they often can exhibit unconventional electronic properties that make them interesting for both science and potential future applications. And the classic example of this would be Z2 topological insulators, which are insulating in the bulk and conducting on the surface. So since the beginning of the field, a central and an enduring question is, how can we determine whether a given material is topological? And in particular, in this talk, we'll be in the setting of real materials. So by this question, I mean, how do we know that, for example, sodium-3 bismuth is a Dirac semimetal? How do we know that sodium chloride is a trivial insulator? And computationally, the standard approach to addressing this question is via first principles calculations using DFT. In the modern materials informatics era, there's now been the emergence of these open source data sets consisting of crystalline materials and their computed properties. And so some of these data sets now have crystal materials and their electronic topology diagnosis. So this allows us to pose a data-driven modeling problem. So given a crystal, can we pass it through some classification model that will predict whether the material is topological or not topological? And we can train this model using a label data set consisting of materials and their binary label, either yes topological or no not topological. And I'll flag that these labels are coming from something known as symmetry-based methods. This will be important at a later point in the presentation, and I'll come back to this topic. So when we began this project, we thought that we would need a very complicated model in order to achieve this task for two reasons. So first, because the broader trend in ML for materials is to use more and more complicated models. And second, because electronic topology is a very complicated exotic phenomenon, and so we thought we would need something very complicated if we could hope to answer this question. What we found is something more surprising, which is that a shockingly simple model can actually obtain over 80% accuracy on this task. And this model is visualized here for you on the periodic table. So the model has just one parameter for each chemical element, and that's shown here numerically and in the scale bar, where blue is negative and red is positive. So for example, the parameter for lithium is 0.49, the parameter for beryllium is 0.915. And these parameters are learned from data. So to make a diagnosis using this model, for a given material, you just look up the parameters for the constituent elements and calculate their weighted average according to the chemical formula. And then looking at the sign of this weighted average gives you a heuristic diagnosis of whether the material is topological or not topological. So we can illustrate this with two example materials. So one would be sodium chloride. And so sodium chloride has two elements, sodium and chlorine. So you look up the parameter values, and since there's an equal amount of sodium and chlorine, we do 1/2 times the parameter for sodium plus 1/2 times the parameter for chlorine. That's 1/2 times minus 0.187 plus 1/2 times minus 2.11. Since that's negative, we predict it's not topological. And second illustrative example, sodium-3 bismuth. Here the two elements are sodium and bismuth. So there's 3 times as much sodium as bismuth, so we do 3/4 times parameter for sodium plus 1/4 times parameter for bismuth. That's 3/4 times minus 0.187 plus 1/4 times 2.167. That's 0.402, which is positive, so we predict it's topological. So now that I've illustrated how to use this simple model, I want to talk a little bit about the physical meaning of these parameters. So for each parameter here on the table, we term the parameter tau e the topologivity of the element. And the reason for that is that the parameter value is intended to loosely capture the tendency of the element to form topological materials, with a greater value corresponding to a greater tendency. And when I say that, I mean mostly in the sense of whether it will tend to form topological materials when bonded with other chemical elements to form a crystalline compound, rather than whether it will be topological in pure element form. And if we look at this periodic table, what kind of chemical intuition can we see? So first, we can see that elements that are close to each other on the periodic table typically have similar values of parameters. And that makes sense because the periodic table structure is such that we expect elements close to each other are chemically similar. Second, we can look at the regions of negative topogivities colored in blue and see that they're clustered in the top right and bottom left parts of the periodic table. So those are the regions of highly electronegative and highly electropositive elements, which typically form ionic compounds. And ionic compounds typically have a large band gap. But in contrast, topological materials will typically have either zero band gap or low band gap. So it makes sense the model thinks that the elements that are typically forming ionic compounds will typically not be topological. So to provide context for the next part of the presentation, I want to briefly zoom out and talk a little bit more about first principles approaches for topology diagnosis. And we can think of there being two broad classes of first principle approaches. The first being direct evaluation, and by this I mean something like Wilson loops. And the second, which has been very important in the discovery of many real topological materials, is symmetry-based methods, as exemplified by the Foucault criterion, as well as more recent generalizations known as symmetry indicators in topological quantum chemistry. And the key thing to know about these is that these symmetry-based methods can greatly reduce the computational cost of performing electronic topology diagnosis, but have the drawback that not all topological materials can be detected using them. And as I flagged some number of slides ago, our model was trained on labels that were generated by these symmetry-based methods. And the next thing we want to do is just see if we can go beyond that and apply this model to identify topological materials that cannot be detected by symmetry-based methods. So to do this, we curate an unlabeled data set that has the property that the materials in this set would, if they do turn out to be topological, we would expect them to be the kind of material that's not detectable by symmetry indicators. Then we use our model to do screening, and if the model is very confident that the material is topological, in the sense that the weighted average of topogivities is above 1, we then perform first principle calculations to validate the prediction. So we perform first principle calculations on 68 materials, and we find that 56 of them are indeed topological, corresponding to a success rate of 82.4%. For comparison, within the labeled data set, materials whose topogivities weighted average is above 1, 93% of them would be topological. And many of these 56 materials are topological materials that have never previously been identified in the literature. And some examples of these newly discovered topological materials are shown here. So the one on the left is a Dirac semimetal, and the 3 on the right are Weil semimetals. So in the time remaining, I'm going to briefly survey some related work that we did after completing this project. So the topology model was, methodologically, this is very simple. It's a binary classifier based on one parameter for each chemical element. And so the first extension is still within this binary classification setting. So we show first that using basically the same method, we can also do metallicity classification with about 86% accuracy. And we also demonstrate that by using chemistry-informed parameter tying, we can reduce the amount of training data that we need to get to a reasonable level of test accuracy. I also want to flag that one thing we found from this was that previously we were surprised that we can do topology classification with over 80% accuracy with just one parameter per element. And actually we find that with this parameter time approach, we actually can do this with even less parameters. And this work was posted on arXiv earlier this year. And the other extension I want to discuss is bandgap modeling. And so here we again use the same idea of one parameter for each element and calculate their weighted average. But now it's not binary classification. So rather than looking at the sign of this weighted average, we instead pass through a ReLU. And this work was also posted on arXiv earlier this year. So I want to thank all of my wonderful co-authors and mentors, without which this work would not have been possible. I'll also be at the poster session today. And thank you for listening. Happy to answer questions.
Any questions for Andrew?
Thanks for the talk. So in the mission of being able to identify new topological materials, is it important that this classifier seems to be agnostic to whether certain elements can even bond with each other? Like you might design some great, you can just pick a bunch of materials that are very red according to that and say, oh, this is for sure going to be topological, but they might not even form bonds. So.
Yeah, I think that it's definitely important to restrict to realistic chemical formulas. So all the data here that we use to train the model and also to do this discovery, it's coming from ICSD. And so I think that some of the intuition that's developed here is related to the kind of bond character that these elemental form. So if you come up with some very unrealistic structures and unrealistic chemical formulas, I don't think the intuition would generalize.
So your method is only based on chemical formula, right?
Yes.
So if I give you C, how do you know it's graphene, graphite, diamond?
Yeah, so the model is agnostic to spatial structure. So yes, you're right that the prediction will always be the same for different spatial structures with the same chemical formula. And this will cause some amount of error to be incurred. I think for the case, so I think that it will often be the case that materials with the same chemical formula, even if they have different spatial structures, their coarse-grained diagnosis in the sense of whether it's topological or not topological will often be the same. Of course, not always. But then if the more fine-grained thing will change more often. So if it's going to be a Z2TI or a TCI, that will change more often. I think that if you want to get a more fine-grained diagnosis, I think the spatial structure will be definitely more important than in this work.
I think it's great method. So for your training, do you only consider compounds like two elements, or do you also consider compounds more than two elements?
Yes, so we also consider materials with more elements as well, but I just illustrate with two element materials since it's faster to show.
So let's say you found that you restrict your training set only to two element compound, and then let's say another model, you only restrict the training set to more than two element compound. Do they give you the different score for each element?
Yes, of course the parameter values will change a little bit if you were to fit it only on 2-element materials or only on 3-element materials or so on.
But the difference is not so important, just quantitative.
Yeah, so I think that we actually do evaluate this question. So in our we didn't do the exact thing that you mentioned, which is fit separate models, but we break down the test performance based on the number of elements present. So there will be some variability in test performance. I think that if you have enough data, you can probably get slightly more refined models if you were to train separate models for different amounts of element counts.
Let's thank the speaker again.